Hello everyone. In this video we're going to talk about how was the first photo of a black hole taken. So if you love physics like I do, watch this video until the end. This is the first picture of a black hole ever taken. It was taken in April 2019 by the Event Horizon telescope from NASA. This black hole is in the center of the Messier 87 or M87 galaxy. That's 55 million light years from Earth. This black hole here has a mass that is 6.5 billion times the mass of our Sun. But you may be asking yourself, how can we see a black hole if a black hole is known for sucking even the light? So let's understand what we're seeing here exactly in terms of physics. Okay, so first, what is this black hole that we see there? So we see something that looks like this. Here in the center we have what we call the event horizon. This is the black hole itself. It's where everything gets sucked, even the light, okay? And it has a radius that we call the Schwarzschild radius. Around here we can see this orange light. That's actually the accretion disk, where all the mass and gases get spinning around here. Any mass, anything that has mass that enters this radius, okay, that passes through this radius here, gets sucked by the black hole. And this radius is actually 3 times the Schwarzschild radius. So everything that enters into this disk here gets sucked by the black hole. Only one thing that does not, and that's light, right? Light actually can go a little bit closer to the black hole at 1.5 radius, Schwarzschild radius, okay? After this point here, even the light gets sucked by the black hole. So this is the picture we're seeing, but actually there's some details here that I want to show you. So what exactly do we see in that picture? Well, we take the event horizon here and start shooting light at it. So all the light gets sucked by the black hole, right? Even the light that passes through the radius, the Schwarzschild radius, gets sucked because this force is too strong. But at some point, the light actually can escape this force here and turn around the black hole. This distance here is actually 2.6 the Schwarzschild radius. And if you remember the image I've showed you before, it's actually greater than the event horizon itself. And that's exactly what we see in the picture. We do not see the event horizon itself because all the light that gets through this radio here actually gets sucked. So what we see is a hole like this. But there's something very interesting and weird that happens with the light and with the picture that we see. So the interesting thing is that, as I told you before, all the light that hits the event horizon, the black hole, gets sucked, and it also keeps getting sucked to the black hole at a distance of 2.6 Schwarzschild radius, right? So imagine here we have the edge of this radius, right? And the light gets sucked also. So the light that hits the front of the sphere here, our map is mapping the front of the sphere, right? But also all the light that goes from here until here, the edge, actually is mapping the back of the black hole. So that image that we see in the center, the black hole we see in the center, is actually mapping the front of the black hole and the back of the black hole at the same time. So what we see there is the front and the back of the black hole. Actually don't see, right? There's no light there, but that size is actually mapping the front and the back of the black hole. Another thing is that you see that one part of the picture is actually brighter than the other, right? This is what we call the Doppler beaming effect. This happens because the matter around here is spinning very, very fast, almost the speed of light, okay? It's very fast. So the mass that's coming towards the telescope, okay, toward us, is actually appears to be brighter than the mass that's going away from the telescope. In this case here, this upper part. So the bottom part, it's brighter because the mass is spinning in a direction towards the telescope. So that's how we see the black hole and how the first photograph was taken. So I hope you understand what we're actually seeing here. And well, now that you know that's possible to take a photograph from a black hole, let's imagine you want to take a selfie from the M87 black hole. So the first thing you need to be aware is that the Schwarzschild radius for the M87 is 1.9 times 10 to the negative 3 light years. So you want to be at least 3 times away from this value, right? That's the accretion disk, because everything that goes in this value gets sucked in, and you don't want it to happen, right? Another thing that you need to take into account is the diameter of the black hole, and that's about 120,000 light years diameter. So let's suppose your front camera, the front camera of your smartphone, has a field of view of 80 degrees. So how distant you need to be in order to take the selfie? Well, we have a triangle here, a right triangle here, and to calculate this distance, we need the tangent of this angle. That's the 60 light years, 60,000 light years, divided by x, the distance from the center of the black hole. And this distance is actually 71,505 light years away from the center. So if you wanted to take a selfie from a black hole, you need to be at this distance from its center. So that's it. Hope you enjoyed, and see you next time.
Thank you for watching this video. Hope you have a great day ahead, and we'll see you later.